design decision can have ramifications that are really painful, because when we designed the network or the IP layer, we were fine with reordering. And then TCP made this decision about cumulative acts and treating multiple duplicate acts as a sign of loss. And because of that now, network operators try very hard not to reorder packets, because they know that if they reorder packets, congestion control at the TCP layer gets confused and will slow its rate, and then users are not happy. And so network designers are now kind of artificially constrained to not being able to reorder packets. This has never really troubled people, because there's something natural if you're sending all your data on one path. It's quite natural that you don't reorder packets, so reordering was pretty rare. Until we got to data centers, where data centers, as we'll study, have lots of parallel paths. And so operators would like to be able to load balance traffic across all those paths. The minute you load balance, you get reordering. The minute you get reordering, TCP gets unhappy. And so data center operators are now thinking about ways to actually fix this. But anyway, long story short, sometimes these design decisions, there's no end to thinking about them deep enough or hard enough, because they have these implications. So that's another downside to loss, is that sometimes TCP gets confused between loss and reordering. And the last one, which somebody touched upon, is that loss follows delay. So you've already suffered delay by the time you see a packet loss. This, again, the early days was considered fine. In the context of data center applications and modern internet services, where we care about low latency, so if you think about self-driving cars, this idea of incurring delay is not something that's very pleasant to people thinking about self-driving cars and real-time automation and so on. Okay, so any other ideas to how we could detect congestion, if not loss? And remember, we're in a host-based regime. What else could the host be looking at? Round trip time, so delay. Right? So as a sender, I could be looking at the round trip time I'm estimating, and if I see an increase, I could say, aha, I suspect that's congestion. For a long time, the idea of using delay in congestion control is a very old one. Even Van Jacobson's paper in the 80s talked about potentially using delay. It was often dismissed because it was considered too tricky to get right. You have to get good delay samples. You have to say, I'm getting an increase in delay, but an increase relative to what? Right? You have to have a pretty good idea of what your normal uncongested delay is like. And then also delay was considered a noisy signal because you accumulate delay along the way. Any node along the path can add a little bit of delay, and then it looks like you have a lot of delay, even though there wasn't really bad congestion. So for all these reasons, for the longest time, people thought delay would be an interesting signal to exploit because it's an earlier signal than loss, but kind of hard to get right because you need to have a lot of delay measurements to get a good, accurate indicator of when delay causes congestion. This has changed quite recently because Google's new BBR protocol is based on delay. And their starting observation, they were doing this in the context of YouTube, their starting observation was that they get a lot of data samples, a lot of round-trip time samples. Because if you're the YouTube server, you're sending out so many packets to so many clients all over the internet that they have a wealth of delay readings that they can build off of. And so they've shown that actually delay as a congestion signal works pretty well. This is still a little debated. This is what BBR does. There's a fair amount of research showing that there are certain pitfalls to this. And so I would say it's new, but certainly a very convincing proof point that you can do delay-based congestion control. We might touch on BBR very briefly next week, but for now we're going to stay in the regime of losses. The only other observation I wanted to make on losses is that not all losses are the same. As we've discussed in the context of TCP reliability, we detect losses one of two ways. One is when we get a certain number of duplicate acknowledgements. This is kind of an indicator of, it's an isolated loss. Right? The fact that I'm getting duplicate acknowledgements means my packets are still going through. So it probably means that there's some mild congestion, but it's not severe. Okay? The other way we detected loss was through timeouts. Right? And so timeouts are a pretty good indication of severe congestion because you sent a whole bunch of packets and you got no duplicate acknowledgements. So your packets didn't make it through. Either your packets didn't make it through or your acknowledgements are not making it through. But whatever the case, you're getting a fair amount of loss. And so this must be pretty severe congestion. And so when we get into TCP, for now I just want you to file this away, that we have, not all losses are the same. We distinguish between a little bit of loss versus fairly severe loss, and TCP will react differently in those two cases. So we'll cover this when we cover TCP. So taking stock again where we are in our design space, we've expanded the host-based, and we're going to focus on loss-based, host-based, dynamic adjustment, congestion control. Right, so with that, where were we? We had our 3 design steps. One was detecting congestion, which we've now decided we're going to look at doing so with loss. Discovering an initial rate, which we'll do now, and then what are your increase, decrease goals. So discovering an initial rate is fairly easy. The goal is to estimate what is the available bandwidth on this path for this flow when it starts up, right? What is a reasonable estimate of the available bandwidth? The way we're going to want to do it is to start slow, right? Because we don't want to congest the network, so we want to be fairly conservative. So for safety reasons, we're going to start by sending a small amount on that path, but we want to ramp up quickly, because if it takes too long to discover how much capacity you have, the available bandwidth, then you're just wasting time and wasting that bandwidth. What do I mean by that? So let's take an example. Let's say what would happen, starting small is fairly easy to understand. Just pick a value that's not unlikely to congest any path and start with that. Ramping up quickly, here's an example of what if we did a linear increase where we said I'm going to add 0.5 megabit per second every 100 milliseconds until we detect loss. The problem with this is if your available bandwidth is, say, 1 megabit per second, you're going to discover your rate in 200 milliseconds, 2 rounds. That's fine. But if your available bandwidth was 1 gigabit per second, it would have taken you 200 seconds to discover that you could be sending at a gigabit per second. And on the internet, any of these could be equally possible. So this is just an example to show you that linear increase would be way too slow for what we want to do because the range of possible available bandwidths is too large. Okay? So the solution we work with in TCP is something that's very poorly named. It's called slow start. The reason it's called slow start is because you start with a small rate. I think small start would have been a better name. So you start with a low value, which would be much, much less than the actual bandwidth. But then because linear increase takes too long to ramp up, slow start is actually going to go exponentially fast. Okay? So what that means is, for example, it's going to double the rate until it experiences loss. So let's say that you had a source that decides to start at 100 megabits per second. So it's going to send it 100 meg for a while, and then it's going to send it 200 if there's no congestion, then 400, then 800. And then let's say at 800 megabits per second, there was no loss, so you're fine. So now it's going to send at 1.6 gigabits per second. And then at 1.6 gigabits per second, it experiences loss. So what the sender has learned at this point is that a safe rate was 800 megabits per second. Okay? Does this make sense to people? So slow start means you start small and you scale up exponentially. Any questions of that? Okay. So the last question is this question of by how much should we increase or decrease when we have congestion? So this is the rate adjustment phase of congestion control. This is probably the most critical part of the solutions we've developed so far. Because how quickly you adapt and how much you adapt by is going to determine how a host adapts to changes in the available bandwidth. Right? If you're too slow to adapt, you're going to be very inefficient in consuming bandwidth. Right? And if you're too slow as well to adapt, it also determines how bandwidth is shared in terms of fairness. Right? So think about this as, I had a link, it was 1 gigabit per second. There was one flow consuming that link, it had the entire gigabit per second. And now another flow joins on that link. If I'm going to be very slow to adjust, then it's going to take a very long time for this new flow to get its half gigabit per second. So how quickly you adjust impacts fairness. It also impacts how efficiently you're using your link. Right? Let's say you started out at 100 meg and your capacity was 1 gig and you were adjusting very slowly. You're probably going to take way too long to fill that link. So we want a good set of increase and decrease rules in order to balance these two goals. We want efficiency, high utilization of the link bandwidth, and we want fairness, which is how the share of the link that each flow is getting. So how should we adjust the rate? You could imagine any options. Something is quadratic or the cube root of some loss, whatever we wanted to come up with. At a high level, there's really, do you increase fast or do you increase slow? And the two canonical approaches are either you increase or decrease multiplicatively, which means you increase or decrease by, let's say, 2x or 3x. So whatever my rate was now, I'm going to double it in the next iteration. Or I'm going to cut it by half in the next iteration. Or a slow increase or decrease would be to add or remove a constant amount. So I add, for example, +1 to my rate, or I remove +1 from my rate. So this gives us 4 design options based on how you're increasing or decreasing. So AIAD is additive increase, additive decrease. Means you increase additively, you decrease additively. So a little bit, you increase slowly, you decrease slowly. AIMD is additive increase, so I increase slowly, but I decrease very rapidly. Okay. MIAD is the opposite. I increase very aggressively and I decrease slowly. And MIMD is I both increase and decrease very rapidly. Which do you think is the right approach, just intuitively? Others? The last one. Interesting. Okay. I'm going to tell you that the answer is the second one, AIMD, that you increase gently and you decrease rapidly. And we'll talk about why. The intuition is that, if you kind of getting it wrong and sending too much is usually worse than sending too little. Because if you send too much, you congest the network, you get loss and you get delay. If you send too little, you're just getting somewhat lower throughput. And so the general approach that we take is that we do a gentle increase when you're uncongested. So it's gently exploring. But when you hit congestion, you cut down very quickly. Okay. So that's additive increase, I increase slowly. Multiplicative decrease, which is I drop very quickly. Most of the rest of this lecture is going to be going into this why AIMD in more detail. And so the way we like to explain this is through a very simple model that I think captures this intuition really nicely, which is, let's say we had 2 flows that are going over a single link of capacity C. Okay. And the share of each flow is x1 and x2 respectively. So we're going to use x1 and x2 to denote the share that flow 1 and flow 2 are getting. What did we say we want here? We're saying that when x1 plus x2 is greater than C, then the network is congested. Right? If x1 plus x2 is less than C, then the network is underloaded, so we could be increasing. And what we would like is both, that x1 plus x2 is equal to C, so we're fully at capacity, and that x1 is equal to x2, which means we're sharing fairly between the 2 flows. Okay, in an idealized world, that's our goal. So let's look at what this looks graphically, with a simple model where we say capacity is 1. What I'm showing you here is the rate that each user has, so x1 and x2 on the y-axis, right? And so 2 users with rates x1 and x2, we say that you're congested if x1 plus x2 is greater than 1. Right? So we have unused capacity, or you're underloaded when x1 plus x2 is less than 1. So on this graph, if you look at the line, where is the line where x1 plus x2 is equal to 1? That's this blue line that we have here. Okay, we call this the efficiency line. If you're at any point on this line, we have perfect efficiency. We're completely using the capacity of the link. Does that make sense? If you're above it, you're congested. If you're below it, you're underloaded. And then we have a fairness line. We said you're fair if x1 is equal to x2. On this graph, that's the green line here. Okay? That's the line where x1 is equal to x2. So really, where we want to be operating is at the intersection of those 2 lines. That's where efficiency meets fairness. And that's our goal. So let's look at a few just example allocations. If I said we had an allocation of x1 and x2 is 0.2 and 0.5, we are underutilized, right? This is inefficient use of the network. If we had x1 plus x2 is 1.2, we are congested. We're overloading the network. If we were at this point here with 0.7 and 0.3, we're actually perfectly efficient, but we're not fair, right? Because they don't have an equal share. And so really, the only place where you get both, again, is when x1 and x2 are both 0.5. So that's going to be our goal. Okay. We're going to walk through all of the 4 different design options here, but let's just a little recap this. I'm not trying to be patronizing, but I know that I sometimes have to rethink how I calculate the slope of a line. So I'm just going to remind you, if we have a point x1, x2 over here, and I say that I'm adding or subtracting some amount from x1 and x2. So I'm going from x1, x2 to x1 minus a and x2 minus a, or adding b to both x1 and x2. What I'm doing is I'm moving along a line that has a slope of 1. Okay, so adding and removing a constant to x1 and x2 all I'm doing is moving along a line that has a slope of 1. If I said I'm